Good morning, it's Mrs. Sharp. This video is to help you with half-life, which is, as the definition says below, the amount of time it takes for 1/2 of a radioactive isotope's nuclei to decay into its products. So, something that's radioactive could decay very quickly if it's very unstable, or if it's not as unstable, it might take a while longer, but each and every radioactive isotope has its own unique half-life. In your notes, you have a chart that looks something like this. It is a graph. If I can find it. There it is. Of what this decay looks like. So if you were to imagine that a radioactive isotope is in red here, you would start off with all of the atoms in the sample being radioactive. But since they're unstable, over time they would all tend to decay and become stable. So the parent isotope, which is shown in red, is our unstable radioactive isotope. I'm going to write that in here. And over time, those are going to decay and produce a daughter isotope, which is shown in gray, which is more stable. And the rate at which it does that is known as a half-life. And according to this graph, after one half-life, you would have half of your atoms now being radioactive because the other half, or 50%, have decayed into a more stable isotope through one of those methods that we've been talking about. So either alpha radiation, or beta, or gamma, positron emission, or electron capture. So through one of those means, 50% has become stable. Again, those are shown in gray. The half-life is down here on the x-axis. After a second half-life has passed, half of the remaining radioactive atoms would have decayed, leaving you with only 25% being radioactive, and the remaining portion being stable. So now we're up to 75% of our original sample. Those atoms are now stable. And so on and so forth. In the third half-life, we're going to be all the way down to 12.5% of our sample being radioactive, and 87.5% being stable. And you can go out as many half-lives as you need to, but the point is that scientists use this information to see how old something is. By working backwards and determining what percentage is still radioactive, they can know the number of half-lives that have passed, and that can tell them how old something is. To do that, though, they have to understand what kind of a sample they're working with, or what kind of isotope they're investigating. So we have a little table here that I'd like for you to put in your notes. And that's not so you memorize the half-lives here, that's so you have the reference. So don't worry about memorizing these or anything, it's just so you have something to use when you need to know these half-lives. So each and every radioactive isotope, or radioisotopes as it's shown here, have its own unique half-life, everywhere from the 6 here, polonium, with a really short half-life of 163.7 microseconds, down to uranium-238, which takes 4.46 billion years to do the same thing. So for polonium-214, it would lose half of its radioactivity almost instantly, whereas with uranium, it would take 4.5 billion years to do the same thing. So the reason that polonium is so quick is because it is much more unstable. It is much more unstable than uranium. Uranium is still unstable, but it is not motivated as much for its atoms to become stable. So it goes about it, in a much more leisurely fashion. So the quicker something decays, the more unstable it was originally. So I'll let you pause this for a second and write the rest of those down. When it comes to choosing an isotope for use in the human body, scientists and doctors have to decide what kind of half-life would be most appropriate. And what they've decided is that you don't want something in your body like uranium that's going to be radioactive for the rest of your life, and you don't want radiation inside of you for the rest of your life. But at the same time, you don't really want something like polonium in you either, because if you're going to have a test of some kind done, like a PET scan or a CAT scan, then if you were to ingest radioactive polonium, the entire sample would be stable before you even had a chance to complete the test. So scientists and doctors have determined that the best types of isotopes for use in the human body are ones that are long enough for the test itself, but not so long that you're going to be walking around radioactive for a time afterwards. So in this case, probably the best choice would be something like radon-222. The MME and the ACT like to give you half-life problems, and they always do so in the same form. So I'm going to walk through a couple of these with you, but there are also several examples on the blog in addition to these, because I'm going to go through these pretty quick. The thing about these half-life problems is that they will either ask you how old a sample is, or how much is left radioactive, or how much is stable after a certain amount of time. So I'm going to go through an example of each. The key to all of these types of problems is first figuring out how many half-lives have passed. If you can figure out the number of half-lives that have passed, then you'll be golden no matter what the question is asking. So this question says, how much of a 20-gram sample of radioactive strontium will be left after 145 years? So what we want to do first is figure out the number of half-lives. Start with the fact that we know 145 years have passed. We use our handy-dandy chart that you just wrote down. And we see that in one half-life, it would take 29 years for one half-life to occur. So if you divide 145 by 29, you would get 5. And the thing about the ACT and the MME is that they always give you a nice whole number of half-lives, so you don't have to use that kind of crazy equation that you might have learned in Algebra 2 and probably forgotten by now. But if you know 5 half-lives have passed, then you're in good shape, because if you know what the definition of a half-life is, then you should be able to determine what happens after each and every half-life. For example, in this case, if 20 grams is radioactive to start with, then after one half-life, only 10 grams should be radioactive. And after a second half-life, you would have 5 grams radioactive, and after 3, you'd have 2.5, and after 4, you'd have 1.25, and after the 5th, 0.625 grams would remain radioactive. So 6.25 of your original 20-gram sample would be radioactive. So if the question were to ask you how much is stable, that would just be whatever is left. So if 20 grams was what you had to start, minus your 0.625 grams that's still radioactive, that means that you're going to have 19.375 grams that's now stable. Okay, so in each and every half-life, the amount that decays is just going to become stable. So nothing's disappearing. It's just that a portion is becoming radioactive, and some of it's going to become stable. So that's one type of question you may see. Another type of question is going to ask you how old the sample is. So here's your second example. Sample of radon contains only 12.5% of its original radioactive atoms. How old is the sample? So this time we know how much is still radioactive. First thing you want to do is to determine the number of half-lives once again. Well, to do that, you're going to assume that the sample was all radioactive to start with, which means you started with 100% of your sample being radioactive. After one half-life, 50% would be. After 2, 25%. And after your third, you'd get your 12.5%, which means 3 half-lives have passed. The sample is 3 half-lives old. Well, that's all well and good, but we would probably like to know exactly how old it is, not in half-lives, but in some meaningful time unit, such as days or weeks or months or years or whatever it happens to be. So what we need to do is then convert that. So if we have 3 half-lives that have passed, then we know 3.8 days is equal to 1 half-life for radon. Again, that comes from our handy-dandy chart. And so if we multiply those two together, you get 11.4 days. So that sample is 11.4 days old. So those are your 2 types of problems that the ACT or the MME or Mrs. Sharp or Mr. Messler may ask for you to do. You have some 3.8 practice problems to do, and remember that if you should need some more examples, there are several more to be found on the blog. Go to westernchemistry.blogspot.com and scroll down to the 3.8 tag along the right-hand side, and it should bring up all of those great examples. So in the meantime, have a wonderful day, and we'll talk to you later. Bye.